today, class, we're going to learn about, you already kind of know about this, and we already talked about it when we did exponential functions, which was the last section. So today's lesson is going to be called exponential growth and decay. Okay? And exponential growth is, we talked about exponential functions which look like they start and they go up like this, and then they go up really, really fast. That's exponential growth, if it looks like that. Exponential decay are functions that start kind of at a high up point, and then they go down like that, but they don't ever really approach zero, because you can never really get to zero when you're multiplying by a number, okay, that is smaller than 1 and greater than 0. That's what happens. Okay, can anyone think of any situations in real life where you might have exponential growth? Exponential growth. Go ahead.
Maybe if there's like endangered species of animals or something, it starts to get more of them.
Or less of them, right? If it's getting less animals, that would be exponential decay. Like maybe the rabbit population, okay, is declining by 10% every year or something like that. So like on this day you'd have 500 rabbits, 500 rabbits, okay? Then on the next day, or on the next, maybe it's decaying, the next year, you'd have 10% less. So the next year, you'd have 450 rabbits, okay? 450 rabbits. And then the next time you'd have 10% less, right? And then you'd have 10% less, and 10% less, and 10% less. But you're never going to get to zero. Do you see why you're never going to get to zero? Because no matter what you take 10% of, you're always getting some value, even though it's very small. I guess with rabbits, once you get to one rabbit, that's kind of it, because then you'd only have half a rabbit. And that would be bad, you know, or 90% of a rabbit, you know, you'd be walking around kind of funny, you know. Okay, good. Anyone think of an example where you'd have exponential growth? Maybe a different situation. How about something with money? Anyone think of a situation with money where you might have exponential growth? Banks, what, Jordan? Exactly. Okay, that's what exponential growth is. That's why they try to get you to invest in bank accounts, because that stuff grows exponentially. Say you start off and you invest $1,000, right? And they say you're going to earn 5% interest per year. That's what it used to be. Now it's like 0.2% interest. So then after 1 year, you'd have 1,000 and, would it be 1,050, 5%? I think that's a B. 1,050. And then on the next year, you'd have 5% more of that, which I think would be, I don't know what it'd be. You'd have to multiply that by 1.05 and get the next one. And then you'd grow on that amount, and then you grow on that amount. And the reason it goes up like this, not linearly, because you're growing, each year you're growing on a bigger amount, you see? So it's going up like that, and that's why they tell you to invest. If you are really smart, what you do is, with investing, is you put in an amount each month, right? Like maybe $100 a month. And that way your percent is growing on, you have something added, and then you're growing on that much, plus the interest you've earned, so it keeps growing and growing and growing. So you make lots and lots of money that way. Well, some people do, not me. I'm a poor starting school teacher. Okay? Anyway, so let's look at some of the examples on this PowerPoint, and we're just going to kind of teach you through these examples, and I think they're pretty good examples, and they're just like the ones in your book. And so here comes the first one. In a certain time, I'm just going to take a picture of it, because that way you could write on top of it without the answers showing up. Okay, so you don't have to write this down. You could just kind of pay attention. In a certain town, had a population of about 13,000 people since 1998. The population increased about 14%, 1.4% a year. Write an equation to model the percent increase. So I'm just going to kind of show you how you do this, okay? You go y equals, this is your initial amount, 13,000. And then you have 1 plus, when I take 1.4% of something, how do I write that as decimal? Yes, sir.
Isn't it what you're doing is you're pretty much adding 1.4% to 100%?
Right. So how do I take 1.4% of something?
1.14.
0.014. You have to move the decimal place, excuse me, 2 places to the left. So it's plus 0.014, because you have to move this, when you're taking a percentage of something, you have to move this to the left 2 places. You knew that, didn't you? Okay. If you take 25% of something, you multiply by 0.25. So, and then, whoops, I want to turn it back to white. Okay, this. And then I raise this to the x power. Okay? And this is the, so what this is, this x, this is the number of years past, when did it start? 1998. And this over here is called the growth rate. Growth rate. You might want to write these things down. Growth rate. And this thing is the original amount. Original investments, I guess. And this is the amount you'll have. Amount after X years. Okay? Years past 1998. You get that? Okay? And the reason there's a 1 here, which Justin kind of pointed out for us, is because you're going to have 1 times 13,000 plus 14% of 13,000. You see that? Okay? And to write this in a simpler form, I could write this as y equals 13,000 times 1.014 raised to the x power, because I can add those 2 together. Now, suppose, so the next question is going to ask you, okay, it's going to ask, look, relate y equals abx, use an exponential function. Let x is the number of years since 1998. Oh, I did that. Let y equal the population at various times. Initial population of 13,000. The growth factor, which is 100% plus 1.4%, which is 101.4, and as a decimal, that's 1.014. So when I wrote my equation, that's the equation that I came up with. Okay? Do you want a minute to write some of that stuff down? Yes? No? Maybe? Uh-oh. Where's my recorder? I can't see my recorder. Oh, there it is. I'm talking for 8 minutes? Man, I talk fast. So now, moving on. It says, use your equation to find the approximate population in 2006. So I'm going to go back here, okay? So how many years after 1998 is 2006? 1998, what would I plug in there? 2006 is 8 years, right? Okay? So what you want to do on your calculator, you want to say, this will tell you how much money you have. So it's 1.014 raised to the 8th power times 13,000. So I'm going to do this on a calculator for you. Okay? And I just, by the end of the year, I should have some calculators that look like those yellow calculators that you can use to do the same thing. Wow, look at that. Doesn't that look cool? Okay, that's a So if I want to do this on my calculator, or even on most of your calculators, work like the same way, I'm just going to go 13,000, okay, times, and you might want to put this in parentheses, but I don't think you have to, because it's going to do the exponents first. 1.014, and I'm going to raise that, use this little caret button. Okay, most of your calculators should have a little caret button on it. Raised to the 8th power. Okay? And if I do that, and then you might have to arrow over to get back down to the level. And this will tell you how much money you will have in 2006? In 8 years. So you would have $14,529 is how much money, and 37 cents is how much you have. Okay? That's exponential growth. So in 5 years, you've made about $1,529, right? Because it's gone from 13,000 up to there. So that's pretty good on your initial investment of 13,000. So let's go back to another problem. Okay, and let's see if I did it right. Oh wow, look at how smart your teacher is. Approximate count. Oh, wait. Oh, that. Why am I talking about money? We're talking about populations, right? Oh well, I got you were again. What the heck is he talking about? Okay, but it's the same thing. Okay, so whether you're talking about money or people, it's the same thing. And so for this one, I'm going to just set it up for you. You're going to set it up exactly the same way. Who wants to tell me how I could set this one up, if you could see it? Who can tell me how you invest $1,000 in a college fund that pays 7.2%? Okay, it's going to be y equals something. Y equals, what's my initial amount? 1,000. Okay. Times, I'm making 7.2%. So what's that going to look like?
1.07.
Very nice. 1.072 is your growth factor. Find the account balance, and this would be your variable. But into that variable, I'm going to plug in 5. Okay? You guys understand that? Yeah? Okay. So same thing, you're going to take your calculator and just plug in chug. And now I'm talking about money, not populations, but it's the same idea. 1,000 times 1.072 raised to the 5 power. Okay? And then I kind of want to arrow over to get back down to the bottom level, at least on my calculator I do. And so after that time, you're going to have $1,415.70. Questions about that? This concerns you. Real life, Stephen. All right. So I got 3 more examples for your learning pleasure. Now, I think I did this right. Let's just go through. Boom, 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 boom. There, I got it right. All right. So now the next problem says, suppose the account above in the problem is paid interest compounded quarterly instead of annually. So this is a little bit different. Have you seen on the banks it said you earn 5% interest compounded quarterly? Have you ever seen that in the newspapers or anything? At the bank? Maybe. You know what that means? Who knows what that means? If you earn 5% interest compounded quarterly, it means every 3 months, which is 1/4 of a year, you earn 1/4 of 5%. You see? Okay? So if it says compounded monthly, you don't earn 5% every month. You earn 1/12 of 5% every month, but 12 times a year. So the way you set that one up, okay, it is, how much was what were we looking at again? What was the amount of money? Compounded quarterly account balance after 5 years. So here it is. So instead of doing 1.072, I have y equals 1,000 times 1 plus 0.072 divided by 4. Because you're earning 7.2%, you're earning 1/4 of 7.2% 4 times per year. And up here, you're going to have 5 times 4. You guys understand why? 5 years, this is 5 years, and this is 4 times per year that you're compounding. So what this ends up being when you put it in your, you simplify things, you get 1,000, 1/4 of 0.072 is 36 divided by 2, 18. 1.018 to the 20th power. Okay? So because you're earning this amount of interest, 1.8%, but you're earning it 4 times per year for 5 years. All right? And so then if you do that on your calculator, you're going to get 1,000 times 1.018 raised to the 20th power. And arrow over and hit enter. And notice you make about $13 more done that one. That's $1,428 and $1,428.75. And so notice that this was $1,450 if you just compound it once a year. This is $1,428, so it makes a little bit of difference, but not a huge amount of difference. Okay? And that's what that is all about. Yes? No? Pregunta? It looks like you're not looking up there. You're looking down in your lap. What's down in your lap? Cell phone? Couldn't be. Couldn't be. You wouldn't be.
Or an iPod. You know, it would be
Or
like
an
any electronic device.
Electronic device. Look, I did it right. So you have 1/4 of 7.2%, 4 interest periods in 1 year. So divide the interest into 4 parts, okay? And then let's get rid of this thing. And so then X up here, instead of putting in 5 for 5 years, it's 20 because you're earning that interest 4 times per year for 4 interest periods a year for 5 years. Okay? So what's the next one? Is the next one exponential growth? Oh, half-life. You know about half-life? You know about half-life? You know about half-life?
Have you guys talked about it in science a little?
Yes.
No.
Who knows what a half-life is? Yes?
It's for like radioactive components.
Yes, for radioactive stuff. It's how many years it takes for something to become half of what it was before. Okay? So it says technetium, whatever that is, technetium 99 has a half-life of 6 hours. That's a pretty short half-life. Because like radioactive stuff, that like really radioactive stuff takes, has anyone ever, I'm going to pause. What you're going to do with this one, you're going to set it up the same way, like y equals a b to the x. This is an exponential function. This is what we've been doing, okay? So y is how much you're going to have left. A is your original amount, that's 80, okay? B is your growth factor. So what am I going to be multiplying by each time if it's a half-life? How do I take half of something? Divide it by 2 or multiply it by What's the same as dividing by 2? Dividing by 2 or multiplying by half. So I could just put 0.5 right there, raised to the x. You see? Okay? And so it has a half-life of 6 hours. How many half-lives? How many half-lives? Lives? Are lives, I think it should be, are in 24 hours. What do you think? If each half-life is 6 hours, how many half-lives are in 24 hours? 4. Very good. So 4 goes in here because there are 4 half-lives in 24 hours. So now you just do this. Y equals 80 times 0.5 raised to the 4th power. So again, you could use your calculator, or you could just take half of 80 4 times. So the first time, what's half of 80? 40. What's half of 40? 20. What's half of 20? 10. What's half of 10? 5. That's after 24 hours, right? And so, or you can use your calculator, and you can go, whoa, what happened? Where'd my stuff go? Uh-oh, I lost it. Uh-oh, what happened? Technical bugs. So anyway, for those of you in the listening audience, this is what we did, 80 times 0.5 to the 4th power, and I get out 5. All right, next problem, and then we'll kind of set you guys free and let you work. Okay? 24 hours, 40 milligrams, 20 milligrams, 10. So they did it kind of the way I did it first. Okay, but you could do it this way. Okay? So here's one, population growth, okay, or population decay. This is just kind of what Justin was talking about, where populations decay after a while. So again, let's do this one. Let's use partial y equals, we're going to do the same thing. We're going to say y equals a b to the x. Okay? Because this is an exponential growth model. And so, so in this case, what's A? What goes in here? There's an endangered species, has decreased 2.4% a year. Suppose there were 60 of these animals in a given area in 1999. What goes in for A? What goes in for A? 60. Okay? Right equivalent model. So now I got to figure out what B is. Okay? So in this case, I want, it's going down by 2.4%. So what I'm going to do, I'm going to take 100% minus 2.4%, which as a decimal, okay, as a decimal, that's equal to 97.6%, which as a decimal, it's 0.976. You guys understand why that is? Okay? Because it's going down by 2.4. So basically, what I'm doing, I'm taking 60 and I'm multiplying it every year. Is it every year? 2.4 by 0.976, and I'm raising that to the x power. So what do they want to know in this problem? Going back, what they want to know is, okay, here's your main 97.976. What they want, this should be raised to the x, not x down there. That's a mistake. Use your equation to find the approximate number of animals remaining in 2005. So going back, okay, this was 1999. So in 2005, what should x be? How many years from 1999 is 2005? Hello? 6. So 6 goes in there. Okay? So after 6, how many endangered species, 6 years, how many endangered species will be left? So you take your calculator again, and you go 60 times 0.976 raised to the sixth, right? And you get 51.86. 51.86. 51.86 of the animals, but since you can't really have 0.86, you kind of want to round that up to about 52 animals, right? Because you can't have a part of an animal. Well, you can, but that'd be kind of gross. All right, so that's the end. Your homework is going to be, it's on my assignment calendar, but it's kind of all over the place. Not really. Not too bad. It's page 441. I'm going to write it up here. Hold on, Justin. Page 441, 2, 5, 6, 12, 16, 18, 20, 26 through 30, 32, 35, 43, and 53, right? So write that down so you have it, and that's kind of going to be it. Because, what was your question there, Justin?